with pleasure to introduce our speaker. So, Dr. will not yet, soon to be Dr. Desheng Zhang. Desheng Zhang. So I've been doing Desheng for many years back. So I never attended this conference. Okay, so Desheng is PhD student. So University of Minnesota. And his primary research focus is on transportation system, especially the deep data analysis in the context of transportation. So Desheng has published several papers and very good conference, including multi-conference such as. And so today, so his talk will talks about the urban cyber physical system. So
okay, thank you for the introduction. And I'm very honored to be here. And it's nice to get a place warmer than Minnesota. So I'm going to start. Today, we're going to talk about the urban cyber physical system, addressing sustainability challenge by urban system with urban data. Hopefully, by the end of this talk, it will be clear why this is important direction in transportation science. So what is the cyber physical system? The basic idea we're going to see is communication, computation, and control integrated, not only in our smartphones, laptops, but also in larger physical systems, such as smart grid, medical devices, manufacturing, transportation, telecommunication, smart payment, and other urban infrastructure. Those systems in the physical world would upload the data to the cyber world. Those data will be processed to get some knowledge, model, and applications to improve the physical system themselves by robust control. Finally, the input system will generate new data, which will be used by the model and application again to improve the further into the system. And my research is focused on the system in the urban area, called the urban CPS. So why urban cities? Because we are in a rapid process of urbanization. Urban people only 3% of our population, and are 55% now, have become 70% in 2050. Such a rapid urbanization leads to several sustainability challenges. For example, the U.S. congestion delay has been increased for the last 30 years, and the U.S. gas consumption has also been increased for the last 30 years, which lead to urban inefficiency and climate change. To address those sustainability challenges, last month, the White House just announced the 160 million Smart City Initiative, which will be hosted by several government agencies, such as the NSF, DOT, DOE, and next year they're going to be $10 million for the CPS program in the in NSF. So based on this context, my research is focused on the urban system around the world. For example, New York City and San Francisco, Washington D.C., Rome, Beijing, Shanghai, and Shenzhen. For example, in the Chinese city Shenzhen, the urban system we personally studied included taxicab, bus, subway, truck, loop sensor, electric vehicle, smart cars, and cell phones. Those are amazingly complex distributed systems interacting with each other at urban scale in real time. To improve those systems, it is essential to study the data they produce. I have been working on several types of big urban data. For example, several TB of GPS data from several thousand vehicles, and several TB of smart car data and cell phone data from a couple million of smart car users and cell phone users. Based on the system and data, our research is driven by this research vision called the data life cycle. The urban system first generates urban data, which are combined together on the cloud by advanced communication. And those data will be processed to get some model and application by high performance computation. And after this model and application will be used to improve the urban system themselves by robust control. And finally, the improved system will generate new data, which will be used by the model and application again to further improve the system. So this is called a closed loop data-driven CPS. Based on this vision, my research supports three components of the cyber-physical system. For the computation part, I designed protocol for faster and efficient data collection. For the computation part, I designed generic model to capture the urban phenomena such as human mobility, travel pattern, traffic speed, passenger demand, and transit supply. Based on this model, we designed a generic applications such as ride sharing, last mile transit dispatching, and navigation to provide a positive feedback to the urban system themselves. In this talk, I will use two highlight projects, human mobility modeling and mobility-driven ride sharing, to show my contribution in a little bit of detail. So this is the outline of this talk. First, I will cover the urban mobility modeling, then mobility-driven ride sharing, and finally, I will show my future work. And for every project, I will cover the introduction, design, implementation, and evaluation. So we start with the urban mobility modeling introduction. This work is published in the Mobicon 14 and the 6 Spatial 15. So the high-level goal of this project is to model the human mobility at the urban scale in real time. For example, in New York City, how many people travel from the downtown Manhattan to Central Park during last hour? This kind of mobility has many real-world applications, such as the urban planning, transportation, social network, and the location-based services. To capture those mobility, several theoretical models have been proposed, for example, the gravity model and the radiation model. However, a key drawback of this model is that they cannot capture urban dynamics and define spatial temporal granularity. Recently, with the upgrade of urban infrastructure, we have many of those real-time location tracking devices become available. For example, the cell phone, our GPS, and the smart cars. Those devices generate massive mobility data, which hold the key potential to revolutionize our human mobility model. Based on those data, several models have been proposed by our community. For example, the model driven by the subway data, bus data, cell phone data, and the taxi cab data. However, a key drawback of this model is that they are essentially driven by small data, which is the small sample collected offline from the single sources, which leads to a biased assembly and overfitting of those models. Before I tell our approach, let me tell a story first. It's called the Blind Man and the Elephant. And the six blind men touch different parts of the elephant to learn what it is. The man grabbed the tail, said it was something like a rope, and the man touched the ear, said it was something like a fan. Clearly, each of them just got a partial view of this elephant, cannot grab the big picture of the elephant. But since they already captured the different aspects of this elephant, it's possible for us to combine this partial view together to get this big picture of the elephant. Therefore, the key idea of this paper is to combine this partial view, which is the single view driven model, for a big picture, which is the multi-view driven model, for better modeling of human mobility. So therefore, the key intellectual contribution of this work is a data-driven model interpretation technique to use the coordinated context to intuitively learn from the multiple views. Essentially, this technique can use to design a model driven by the data collected from the urban scale, online, from the multiple sources. This kind of model fits the classic definition of big data with high volume, high velocity, and high variety. So the key feature of our data is variety. I will use the data collected from the Chinese city Shenzhen as an example to show the variety of our data. The first data we use here is the cell phone CPR data, which is called a call detailed record. Every record gives us a super ID, a time, a serial number, and an activity, a phone call, a text message. Based on the serial number map of a city, we can have origin and a destination for a cell phone user. The second data we use here is this text cab data. Every record gives us a vehicle ID, a time, a location, and a status with passenger or without passenger. Therefore, based on the trace of the taxi cab, we can have an origin and a destination for the taxi cab passenger. And for the subway and the bus passenger, we use their smart cards to track their origin and the destination. Every smart card record gives us a smart ID, a time, a station, and an activity. Getting in a station or get out of the station. So based on the station map of the city, we can have an origin and a destination for both the subway passenger and the bus passenger. So after introduction, I will talk about the design. We use a mobility graph to capture the urban mobility. And every vertices indicate a location with our partition of the city. For example, we have one location A and location B. And the one edge into two vertices together indicates the number of people traveling from A to B during a specific time T. For example, based on a specific data set, the taxi cab data set, we know there was 10 people travel from A to B during last hour. Okay. So with this mobility graph, we can use the transportation as a view to describe the human mobility. For example, we can combine the mobility graph obtained by the taxi cab data, bus data, subway data, and the private transportation data to get this comprehensive human mobility graph during a specific hour. However, a key challenge for this approach is that currently there's no urban infrastructure can capture the traffic transportation in real time at the urban scale. Therefore, this transportation wheel is incomplete. Alternatively, we can use a cell phone as a wheel to describe the human mobility. For example, we can combine the mobility graph obtained by the data from active cell phone user and the inactive cell phone user to infer the human mobility graph by assuming everyone has a cell phone. However, in this wheel, the inactive cell phone user's mobility graph cannot be obtained because they do not generate any data. So, the key challenge we have here is that our wheel itself is incomplete. And this incompleteness is uncertain for different spatial temporal contexts. However, every view is complementary to each other. So in this work, we try to combine those different views together to design a multi-view learning technique to infer the human mobility graph. The existing multi-view learning assumes every view itself is complete. But in our case, our view is incomplete. So in our elephant story, so every transportation modality gives us a small picture with a high resolution about this elephant. But the cell phone gives us a big picture with a low resolution of this elephant. So our key idea is how to combine this small picture with a high resolution and this big picture with a low resolution together this big picture with a high resolution. So I'm using the mobility from A to B in a specific time t. For example, from airport to train station, we call the X star as an example to show how we capture the human mobility by this mobility graph. We do it edge by edge and we combine them together for a specific spatial temporal context. And for example, I have K different views. Cell phone could be one view, transportation is another view. In our implementation, K is equal to 2. And for every view, we have a normalized mobility observed by this view alone. We call it xk. And for every view, we also have a wk, which indicates the completeness degree of this particular view k. And based on our data, k and xk are given by the data themselves. But the x star, which is the ground truth we try to infer, and the w is unknown. So we try to design a joint optimization to infer the x star and the w together. Our technique is that we use a loss function to describe the distance between this unknown ground truth and the xk observed by a specific view k. And we time this distance with this view completeness degree. Then we do this for all the views. Then we combine them together. Use this as an objective function. It indicates overall weighted deviation from the ground truth. We try to find the x star and the w that minimize this objective function as our solution under the regularization function. So the rationale behind this objective function is that we will have a high penalty if a more complete view deviates from the truth, but it is okay for a less complete view deviate from the truth. So we developed a iterative learning process based on the block of design to address this joint optimization. We have initialization about x star and the w based on the average value of xk. And for step 1, we fix x star and optimize w based on our objective function. For step 2, we fix w and optimize x star. After we have this optimized x star, we go back to step 1 to further fix x star and optimize w until the result converge. So the next question becomes, can this result converge, which is based on what kind of loss function and the regularization function, conjoint function we use. In this work, we use the standard normalized square loss as our loss function and negative log function as our regularization function. Based on the property of, we can prove that those two functions are essentially convex. And based on the property of the block-oriented descent, this convergence is guaranteed. So this is how we obtain this specific mobility from A to B in a specific time t. We call x star. And similarly, we can have this x star for ACT and CDT. Then we combine them together to get this comprehensive human mobility graph at urban scale in real time. So after design, I will talk about implementation. We implement our model based on our collaboration with the Chinese Computer Science and the Shenzhen Department of Transportation. Essentially, we collect 4 kinds of data: cell phone, bus, subway, and taxi. This figure gives the number of residents captured by those 4 kinds of data sets on 24 hours a day in 5 minute slots. And based on this data, we can easily identify the morning rush hour, the lunch break and the evening rush hour. So we use those data will be processed by two clusters in Shenzhen and Minnesota Supercomputing Institute. And the software we are using is the Hadoop Swarm K and High. So before we get this mobility graph, we have to decide what kind of spatial temporal granularity we want. In this work, we use a Shenzhen urban region partition proposed by the Shenzhen government to do the modeling at the urban region level. And this gives the partition. Different color indicate different density. As we can see, the downtown area and the airport area has a pretty high density. And we do the model for every hour. So based on this spatial temporal partition and one data set, for example, the cell phone data set, we can have this result of our human mobility model. And every point indicated urban region. And one edge into two vertices together indicated the mobility between two regions. And the different color indicated different urban districts. As shown by the yellow vertices, we have lots of mobility around the downtown. Similar to this model driven by the cell phone data, we can also have this model driven by the transportation, different views. Then we combine them together to call this model MCAT, which is the short for mobility pattern as our final result. This is MCAT. So after we implement our model, we evaluate our model with 3 months of data for those 4 kinds of systems. And we compare our model with the ground truth, which is obtained by our cell phone location updating data set, which allows the cell phone user for its location for 15 minutes, even without the cell phone activity. So this is the result for the ground truth, and this is the result for MCAT. For some visual comparison, we can see that we underestimate some mobility at the residential area and overestimate some mobility at the downtown area. In addition to this ground truth, we also compare our model with a model called WIR. So we have two kind of curve for two models. WIR is a single source data-driven model by the cell phone data. And the x-axis is the 24-hour day. The y-axis is the percentage error, which is a metric called MAPE. And as shown by the result, for the early morning and the late night, both model has a pretty high error rate because we do not have the public transportation during night time, and we do not use the cell phone a lot. But for the morning rush hour and the evening rush hour, the performance become better because we have some commuting pattern there. And during the daytime, the performance become more serene because the random mobility during the daytime. This work has several board impacts as we using for get some grant proposal from NSF and several awards. I was invited to do several talks at different places. And most importantly, we convinced our collaborator to release 20 GB of the urban data for the benefit of the research community, and we received lots of compliment for that. So the big picture of this work is to use 4 kinds of urban systems with a multiple learning to infer the urban phenomenon, human mobility. We generalize this idea to use more urban systems to inform more urban phenomena, such as the traffic speed, travel pattern, passenger demand, and transit supply, with those incomplete yet complementary data sources from the urban system. What is interesting about those urban phenomena is to combine different phenomena together. For example, we use a ratio rho, which is the passenger demand over transit supply, to draw this heat map. The darker the area, the higher the passenger demand, the lower the transit supply, which motivated us to design some data-driven applications such as ride sharing to address this urban inefficiency. So after the urban mobility modeling, I will talk about my next project, also mobility-driven ride sharing, which is published at the Census, which is the top company for the sensing system. I will use the text type system as an example to motivate the work, and then generalize our idea to border logistics, such as the private vehicles and the logistics. So the high-level goal of this project is to improve the urban mobility efficiency, to try to reduce the traffic congestion and gas consumption. For example, in New York City, every taxi is equal to 20 private vehicles in terms of the cruising mileage, because they keep cruising the street. And all the taxis in New York City consume 32 million gallons of gas every year, which is more or less a middle-sized country such as Central Africa. And another interesting we found about New York City is that there are only 1.3 passengers per trip during a year. And we found that if we use a sedan, 70% of the capacity is wasted. And we also found that there's lots of similar travel methods. Lots of passengers go from a similar origin to the similar destination during a similar time. So a clear solution is to share this kind of unused capacity. The existing, which is the ride sharing or carpooling. The existing ride sharing work, such as the T-share and the Uber pool, they typically use linear programming, and they do not consider overall urban mobility. Therefore, in this work, we argue that right now we have this multi-source urban data become available, and we can combine this individual passenger request with the collective taxi supply, and along with the overall urban mobility to design a practical ride-sharing service. We call it co-ride. And the key intellectual contribution of co-ride is a multi-source data-driven sharing framework. It has a bounded online approximation, has a real-world implementation, and a multi-scale evaluation. So after the introduction, I will talk about the design. So we implement co-ride with the three components: passenger client, cloud server, and onboard devices. Every taxi has onboard devices. It will upload its real-time status to the cloud server, for example, without the passenger, the real-time location. And together with other urban infrastructure, the cloud server will monitor the transit supply and the passenger demand at urban scale in real time. If a passenger wants to do a ride sharing, this passenger submits a request. And based on the passenger's request and the status of all taxis, the cloud server will calculate the schedule and decide the fare, and send the schedule and the fare back to the passenger client and onboard devices. So in this talk, I will focus on my intellectual contribution about this schedule calculation here. So I will use the example of those passengers from the same origin to different destination to show a key component of our design. But our design can also be generalized to the multiple origins. For example, I have 4 passenger requests from A, B, C, D, E. Those are locations. And we formulate those requests to become a request graph. And the way to indicate the real-time travel mileage or travel time based on our urban mobility model. And based on this request graph, we want to get a delivery graph, which is a connected graph with a scoop structure. So every path indicates a shared ride. For example, the passenger go to B, take the taxi alone, or the passenger go to E, C, D, they take the taxi together with a shared ride. Okay. So we formulate this problem as an optimization problem. Based on this request graph, how to get this delivery graph with the minimum weight, indicate minimizing the mileage, or minimal branches, which indicate minimizing the number of cars used for the ride sharing, which reduce the congestion. And we consider several real-world constraints, such as the vehicle capacity, travel period, and port delay. And we proved that this problem is NP hard by reducing the traveling southbound problem to our optimization. And we provide an online approximation algorithm to address this issue. Essentially, the key idea for our algorithm has 2 steps. The first one is passenger assignment based on the minimal spanning tree. For example, based on this request graph, we can have a minimal spanning tree. And we assign a passenger within the same subtree to the same vehicle. For example, the passenger go to E, C, D will be assigned to the same vehicle they go to. And based on this passenger assignment, our second step is order calculation with depth first travels. For example, based on this passenger arrangement of vehicle 2, we have 3 passengers. We doubling the edge, we enable a traversal, and we use the traversal sequence as our delivery order. Combine this schedule vehicle 2 and the schedule vehicle 1, we can have a delivery graph based on our request. So this is the offline version. For the online version, based on our existing delivery graph, we try to add the new request to this graph. For example, we want to add this new request add to the existing graph. We found the closed request C, link C to F. Then for this new request add, we found a set of the closed request, which is closer to F than any other request already in the delivery graph. For example, C and D. For every those kind of closed request, those pink point, those pink vertices, we adjust the structure of the tree, structure of the graph for the smaller weight based on the existing graph. For example, we can add this edge from F to D and the delivery edge from E to D for a smaller weight. Okay. So what's interesting about this online version of our algorithm is its time complexity. For example, for every one of those k close requests, we at most are going to adjust n existing requests for the smaller weight. So the time complexity is k times n. But essentially, we can prove that the k is smaller than 7. Therefore, we can have a linear complexity, which is O(n). I'll give you some high-level information why k is smaller than 7. By the definition, k is a set of the closed requests, which is closer than the new request f than any other request already in the dealer graph. For example, this new request 7 cannot make it into this closed request because 7 is more closer to 3 and 4 than the f. And this more closer request 8, which is closer to f, will disqualify the existing closed request, for example 3, make this maximal set of the closed requests at most 6. So k is smaller than 7. And we also structural analysis the performance of our algorithm to show the key message that we try to show our mileage is at most 2 times of the optimal mileage obtained by the integer programming. Our mileage is obtained by our approximation. And I'll give some high-level information here. Our mileage is x. It's smaller than this traversal t prime because we shortcut t prime to get x. And this t prime must be exactly equal to 2 times the minimum spanning tree. This is how we do the traversal on the minimum spanning tree. And based on our definition, our optimal solution is a minimum spanning tree. So t must be, since the t is the minimum spanning tree, it must be smaller than the regular spanning tree O. So that's why how we connect our approximation solution x to the optimal solution O, which is x smaller than 2O. We have a fixed solution bound of 2. Just consider several constraints. For example, based on this request graph, we can have this spanning tree, which indicate we have 2 subtree with the maximal size of 3. The second subtree has 3 vertices. And it indicates we have to use 2 vehicles with the capacity of 3 to derive the capacity. And therefore, we control the spanning tree, the shape of our spanning tree in different constraints. The subtree count must be smaller than maximal vehicle capacity, and the maximal subtree size must be smaller than the vehicle count. And the travel order and the tree structure will be decided by the travel period and the point delay. So the details in the paper. So after the design, I will talk about the implementation. We implement our Copilot system by 3 components on cloud server, passenger client, and the onboard devices. They talk to each other through the cellular network. We develop an app for passenger in Shenzhen, which can be used to find a nearby taxi, do ride sharing, and call for pickup. And we were part of the team to develop this onboard devices for Shenzhen taxi cab network. It has called the taxi box. It has 3 components: central control, external devices, and onboard sensor. All 14,000 taxi cabs in Shenzhen are equipped with this basic version of the taxi box. Among them, 100 taxis is equipped with the full version of the taxi box with this online sensing part. So after the implementation, I will talk about our evaluation. We have done a pretty thorough evaluation here to show different factors to our ride sharing scenario. For the first factor is the scale. We try to different scales such as regional scale, urban scale, and national scale. And we try to different logistics such as the taxi, private vehicle, and the truck. And we also try to evaluate the impact of different locations. For example, for the city in North America, for the city in Europe, and for the city in Asia. I will start with the scale. Our first evaluation is at a regional scale. We have a field study in Shenzhen with 3 vehicle 12 passengers for 31 days. So every passenger can tolerate 5 minutes of delay. We select one urban region with a high passenger demand with low transit supply to implement this field study. And those are scenario pictures. And we use a metric of this compass, pretty straightforward. For the percentage to reduce the mileage. So on this 31, this graph gives the result. The x-axis is 31 days, or 31 bars. And on average, we can reduce the mileage by 49% by coupling different passengers together for 31 days on average. After this regional scale, we also did a truth-driven simulation on the urban scale. We used the tax cap data from Shenzhen with 14,000 tax cap 6 months of data. We do this truth-driven evaluation, and this gives a visualization of the ride-sharing traces, and this gives the result. The x-axis is the torrented delay. For example, if you want carpooling with another passenger, you have to torrent a certain delay to deliver another passenger first or deliver you first. And the y-axis is reduce the mileage. And if a passenger can torrent a certain 300 delay, which is 5 minutes, we can reduce the mileage by 45% in this whole Shenzhen area. And the second level of our evaluation is this national scale evaluation. This is a Chinese express map, and it links all the major cities in China, like Beijing, Shanghai, Shenzhen. For this highly populated area, we use a 50,000 commercial vehicle network to show the performance of our ride-sharing evaluation. And this gives us 1 day ride-sharing traces. And as we can see, there are not specific city cluster like Beijing, Shanghai, and Shenzhen. And this gives a result. Since we do the ride-sharing at a national scale, we try to combine their cargo together. We have told a longer time in terms of hours instead of seconds compared to the urban scale. And for this national scale, if a driver or a company can tolerate the 24-hour delay, we can reduce the mileage by 19%. After this commercial vehicle network evaluation, we also use a 300,000 private vehicle network to show their performance on the ride sharing. And it's interesting to see this also gives their 1 day ride sharing traces. It's interesting to see the difference between the commercial vehicle and the private vehicle. For the commercial vehicle, those trucks are mainly focused on the national expressway or highways, so their travel time is pretty long, travel distance is pretty long. But for those private vehicle, their travel distance is pretty short compared to the commercial vehicle, and then they're most focused on those big cities instead of those national highways. So after the impact of different scale, we also do the evaluation to test the impact of different logistics. We use 3 kinds of vehicle network in Beijing. This gives their 1 day ride sharing traces. And the blue point indicates the private vehicle. The green is the truck, and the yellow is the taxi. And for the private vehicle, they mostly focus on their workplaces and homes. For the taxi cab, they just spread out the whole urban area. And for the truck, they mostly use those kind of ring route on the highway. And for the private vehicle network, we can reduce the mileage by 24%, 31 for the truck, and 37 for the taxi. Our biggest project so far is this one called a Tale of 6 Cities, which uses more than 40,000 vehicles to infer the carpooling performance in 6 taxi cab networks around the world. And this is the ride-sharing traces for New York City. You can see there's a lot of ride-sharing opportunity in Manhattan, LaGuardia, and JFK. And on average, you can reduce the mileage by 43% of mileage if every passenger can tolerate 5 minutes of delay. And we have visualization. It shows 1 day visualization of a ride-sharing case in New York City with 13,000 taxi cabs. On the left, we have this ground truth, which is the non-carpooling situation. On the right, we have the carpooling situation. Every blue point indicates the drop-off. You can see in the morning rush hour, there's a lot of drop-off at the Manhattan. And we combine the drop-off and the pick-up point for the carpooling situation to see how much traffic we can reduce with the ride-sharing service. As you can see, the density of the ride-sharing is not about the ground truth. And on the top, we have the 2 curves to show the cumulative mileage for 2 different scenarios. As you can see, the purple line, which is the ground truth, is always higher than the carpooling situation, which indicates our carpooling can reduce the cumulative mileage. Yes, yes, yes.
There is their inconvenience is also
Exactly. That's why you have to satisfy some time or distance by copying the knowledge. Yes. So the second city is the San Francisco. You can see there's a lot of cropping opportunity in the downtown as a whole and OAK. You can reduce the mileage by 19%. And then Rome, you can reduce the mileage by 21, not alternate at the downtown and to the airport. You see, then Beijing, and 37 for Beijing, and for Shanghai is 31 for Shanghai. And the last one is for Shenzhen. For Shenzhen, we have three kinds of taxi. The urban taxi, they can travel all over the area. The suburban taxi, they cannot get into the downtown for the Shenzhen. And the electric taxi, which is about 800 to 1,000 electric taxi, they can travel any places, or they will focus on those kind of nearby the charging station because they have to be charged for every 6 hours after the operation. So, summary of our evaluation. For different scale, it's seen that the larger the scale, the lower the benefit, which due to the spatial constraints here. And for different logistics, because for the Beijing, there's one case in Beijing, and for the commercial vehicle, they have better preference than the private vehicle, which may also because we only have limited information, data about the private vehicle. If I have more data, we believe this ride sharing in the private transportation network are more promising. And for different locations, we have found the three key factors: tourism feature, population, and the vehicle, taxi vehicle number. They have the biggest impact on the performance of the ride sharing. After we published our paper, we received an email from a startup company in Dallas. They want to commercialize and implement our service in their taxi cab network in Dallas. So that's why we're trying to work with them to design a flexible and ride sharing service in Dallas. So this is an app you can use to select a vehicle, select a ride, and decide to accept or decline offer. The big picture of this work is called the urban sharing economy. We used to have a book and the DVDs. Right now we have Uber, Airbnb, and Zipcars, both new service. So our key intellectual contribution here is optimization for the real estate sharing, and we use the infrastructure support to increase the benefit. And we have some groundwork for the border logistics, like private vehicle, truck, and at different scale, and the commercialization, potential commercialization. And the next is my future work. And my future work still has most fundamental challenge in our urban central physical system. We try to design and deploy feedback-based application based on the heterogeneous model from imperfect data. The data we collect from the urban system are far more from perfect. They are sparse, they are implicit, they are unhappy. And based on this data, the model we have here is heterogeneous in terms of different scale, different timelessness, and different granularity. Even when we have this perfect model, the service, the application we design is still challenging because we need some domain knowledge and we need some real-world platform. So my first research direction is this imperfect data inference, some approach including the tensor decomposition-based data fusion. The second is heterogeneous model integration, some technical approach include semi-supervised multi-modal learning. And this last direction is the feedback-based application, which is based on a robust model data control. I will use three simple slides to show the three directions in a little bit of detail. The first direction is the imperfect data inference. We are working with our collaborators in Shenzhen trying to do a bus arrival prediction with a high accuracy. And the premise version based on the text type GPS data, based on the bus GPS data, has been used by more than 100,000 users. And this graph gave their request account for 24 hours. And but the key challenge we are key for this application is that the imperfect bus GPS data. So the bus GPS data got lost all the time, especially in the downtown area with the tall building. So we try to use this multi-source data fusion technique to address this issue. Try to combine the text cab data nearby and the smart car data, which indicate some users just get on the bus. And some technical approach, including the context-aware tensor decomposition, we try to minimize the recurring error with this technical approach. The second piece of future work is the heterogeneous model integration. And the goal of this project is that we try to do a real-time energy modeling at the road segment level. The key challenge we have here is to find special temporal granularity. We try to model the energy at the road segment level in real time, and also we have lots of private vehicles. They don't have any data for us to infer their behaviors. So in this work, we try to use the existing commercial vehicle data combined with the existing urban infrastructure, such as a cell phone, loop sensor, and the camera to infer the energy consumption. For example, with this loop sensor for a specific road intersection, in the morning we can see when the traffic goes up, the speed goes down. But the key challenge is that those loop sensors only installed at limited locations. We try to use this commercial vehicle data with the existing urban infrastructure to infer the behavior of a private vehicle. So we try to do this semi-supervised multi-learning, such as a co-training, to minimize the disagreement between different models. So this gives some preliminary result based on the text type data. So every yellow road segment indicated a higher energy consumption. This is in real time. Our last piece of this future work is the feedback-based application. We are working with Department of Transportation in Washington, D.C. for their capital bike share network. And the goal here is that we want to do efficient bike rebalancing. For example, in some station, let's give a station map of the ride-sharing system in Washington, D.C. Our point indicates a bike station. The bigger the point, the higher the demand. For example, in this station, we don't have any bikes, but we have lots of dogs. For some stations, we have lots of bikes, but no dogs. For this situation, we cannot rent a bike. For this situation, we cannot return a bike. So right now, the operator tries to use those trucks to do the bike rebalancing, to move some bike from one location to another location. But right now, they are doing this ad hoc. They just use some experience and to do this heuristical bike rebalancing. But we try to model this kind of behavior of the bike user to do a more efficient bike rebalancing. The key challenge we have here is this dynamic model passenger demand. And the key technical approach we try to use here is a robust model predictive control. We try to model the passenger demand and the transit supply uncertainty. We try to minimize the rebalancing cost and the supply demand mismatch. A summary of this talk. First, to give introduction about the urban mobility modeling based on multi-learning. We have real-world implementation. And based on this mobility model, we design some mobility-driven ride sharing. We have an optimization framework. We have some potential commercialization. And for the future work, the first direction is the imperfect data inference. The second is model integration. The last one is feedback-based application deployment. So in this short talk, I use 10 different urban infrastructure to show my contribution, to show our contribution. And the key message I'm trying to deliver in this talk is that those are amazingly complex distributed systems interacting with each other at the urban scale in real time. Those systems can be used to infer some real-time urban phenomena, which can be used to design some practical application to address both the pressing concern about our urban sustainability. So I will take a moment to thank all the PI work with me, all the students work with me, and I will take some questions if there is any.
I have a question about your car sharing algorithm. I think that your proof is based on the non-constrained version of the problem. But after you adding those constraints, is that still two approximations?
Yes, very good question. That 2% does not hold. We use the branch and the bound to let constrain the version of the ride sharing.
I see. So it's the very reasonable one.
I'm trying to get a broad picture of this. So you have the real-time data, which is good, and you have it at a large scale to build the model. I'm trying to relate with the context of machine learning. So as I understand, correct me if I'm wrong, this is a part of supervised learning, right?
semi-supervised.
Semi-supervised.
Yes, only limited label data. For some situation, we don't have any label data at all. Because this is pretty tricky because the data is collected not for our research. It's collected for the building purpose. For example, the cell phone data and for the management data. And we have to, as an example, we have to infer the ground truth based on our certain technique. They do not directly tell us something we want to know, but they are pretty valuable in terms of research. Yeah.
So this is a part of semi-supervised learning. And so I was talking to you about train and test.
Yes, yes.
So you train your model based on the data that you have. And so the testing that you do
It's
is
a different data.
It's a different.
Yes.
So it's an out of sample
Yes.
testing that you are doing. That's a different data
Different
set.
data. Yeah.
Okay.
So, where is the what is the multi-view setting? From the like the optimization framework, it sounds more like a setting. So, I've been working on this array. So the basic idea is that we have multi-source of data, but each source itself is sufficient to compete.
Yeah.
But however, the reliability is not
Yes.
as the unreliable.
Mhm.
So therefore, we want to look at all the sources together to find the true information. So therefore, typically we want to weight each source based on the reliability. Right?
Yes.
But this is different from the multi-view learning setting, where each view just gives a subset of information of like, for example, like the traffic volume application you mentioned, so there are like subway traffic,
Yes.
traffic transportation, traffic transportation. Then you need to aggregate their counts. So each view itself is not sufficient enough. But if you consider multiple source, like multiple channel agencies, they may give a complete count, but just the count number could be inaccurate. Then you can wait. But the multi-view probably want to aggregate instead of the second weight.
Or when the other side different view are independent from each other. For example, the cell phone view is independent from the transportation view because no matter what kind of transportation modality you are using, you are still using your cell phone. So our
So
side,
when you infer this traffic, like traffic volume, like the mobility, do you need to aggregate their counts?
we need to aggregate within the transportation view, but we do not aggregate the transportation with the cell phone.
Yeah, but I mean the formulation like W and I the loss function.
Yeah, that's why.
Or aggregate.
I think it's aggregate both view.
So you are, so that one is just aggregating transportation.
Yes, that one.
Oh, so it's not like different.
Yes,
ways.
no. Okay. Good question. Any other questions?
Is all the data available for open source, or it's very
As I said in the talk, I convince our collaborator in China to release partial data. We cannot release the whole data because it kind of first of all very big. Then it's not pretty sensitive and some privacy information there. We are only using this data for the mobility modeling, but it can be used for other purposes. So we only release the data related to our mobility modeling part. It's the time, location, and the passenger ID. It's just a serial number. We cannot just like to every individual passenger. And we do it at the region level instead of the road segment or GPS level. It's on my website.
Like you say, you do not have the information for the private cars.
Yes.
So is there a solution which you're working on to get that information, for example, like GPS trackers or something like that?
For different scenarios, when we do the first mobility modeling part, we do not have anything with the private key. But right now, after we do the ride sharing, we talk to several GPS providers, they got some sample data about the GPS data, the GPS navigator. That one is installed in the vehicle. So we kind of have the private vehicle information, but it's not, in Shenzhen, I think that city we have 20 million, 300 million private vehicle. We only have a couple thousand of the vehicle with those kind of navigators. So, yeah. It's a very biased data. Any other questions?
So I have a question regarding your evaluation using collinear as the ground truth.
So, I mean, all you get from there is a cell tower, right? Let's say, so just from a cell tower, I mean, the range is a circle of huge number of miles. So, how fine range is that one?
And we do it at region level. And for the region level, the cell phone data give us the location for the user at this cell tower level. And we have a region that cover several cell towers. And for this cell tower, it will tell us when you make a cell phone call, you send a text message and have the internet access. We have a complete trace of every individual users. Then we use some existing technique. We try to divide those complete trace into different region, different segments. Then based on every segment, we have origin and destination at the urban region level. Right now, it's pretty fine, but we do it at the region level because for this one is okay, but for the subway and for the bus, we cannot have this fine spatial granularity.
So, in terms of square miles or square kilometers, how much?
In Shenzhen, we have 2,000 square kilometers. We have about 10,000 cell towers. But for the downtown, it's more dense than the suburban area.
What is like the prediction that you make? Like how much of error or ambiguity would it have? In fact, even your ground truth would have certain square kilometers, so you can predict. You don't know where within that region where it is. So how much is that?
We do evaluation at the urban region level. Our region is about 3.5 square kilometer. Okay. Actually, the size in the setting, yes. Yes, yes. They have different definition for mobility, and we try to use because our different data set have different features. We try to find a common ground for different data sources to model the mobility at the flat level. The cell phone can tell us the more detailed information, but the bus and the subway cannot. So that's why we we model the mobility at the region level instead of this fine-grained cell tower level.
Do you have data on where people are going, what kind of establishment, and what kind of activity they do?
No, we only have a location type and a serial number for different users. Okay, thank you. Control.